Hello. Today we're gonna talk about L2 projection implementation. I do it in Godot. Here's example of some 2D function approximation using L2 projection. But we will start with one-dimensional problem and then extend it to 2 dimensions. In fact, there's a kind of huge gap between how difficult it is to implement one dimension, and there's a huge gap between implementing skill gap in 2 dimensions. So in a sense, I wanted in this video not to go like the simplest route and show you like 1D because it is very simple, and then 2D. So I kind of want to diffuse, homogenize our kind of skill requirement and implement an intermediate step where I try to basically show how to do 1D case using methods which I will explain and use in 2 dimensions. So beyond that, since I've already gotten some nice results in 2 dimensions, including simple FEM simulations, I wanted to also include some portions of video that will kind of incorporate some like requirements, some elements from these harder tasks. So I kind of wanted to mention them here so it's easier to understand them later. And one of these things is basically 2D meshing. In order to do even L2 projection implementation in 2D, we need some kind of discretized space. And it's another topic. It's super huge, it's interesting, but it's also very, very hard. We will have to implement specific data structures and algorithms to generate this mesh. So in this video, I also kind of wanted to talk about that and also implement it so it's easier to understand later. So as I've gotten some more experience with FEM, my kind of understanding of what is L2 projection changed a bit. So in practical sense, I see it more of a stepping stone between actually realizing the FEM model, working at least, because like really in practice, if you try to implement FEM model from scratch and something doesn't go according to plan, basically you don't know even where you made the mistake. And kind of this L2 projection is a first non-trivial case of actually getting the system working. So you assemble this matrix, you solve this matrix, you assign values to your nodes, and you can visualize some kind of solution. So it's very useful, I think, still to go through this process. So today we will discuss. So first of all, I will return to topic of our previous video where I tried to explain my intuition for L2 projections. We'll clarify one thing there, and then we will kind of change the way of thinking which will affect our implementation. So notice few things, and then we will kind of go through one-dimensional case, how it's done in a book, and then we will try to expand this idea a bit, kind of overcomplicated it may appear, but then we will kind of trivially implement it in 2 dimensions, although we will have to get some kind of mesh, I will kind of generate the most simple example, so we don't have to go into meshing. So yeah, let's start probably with this first point. What I wanted to clarify. So okay, I've tried to give you my kind of intuition that L2 projection is kind of the most viable solution, basically based on what kind of basis vectors we have, right? And then I kind of compare them. Okay, these expressions look very alike, but I didn't go kind of mathematically why it's so, and I won't go deeply here today. But only thing I wanted to mention is that how do we get from this particular expression, that this is the definition of our L2 projection, into this expression that says that we have to have a system of equations. Like, okay, so in just how I see it purely mathematically, no intuition, nothing, is that by this definition, we should have some kind of, as I remember, it was probably the test function v that have some kind of requirement that it has to be in this function space of piecewise linear functions, whatever. And so this expression should hold for any function v that's in that kind of space, in this collection of functions. And what I kind of propose, let's expand this function into a series of our linear combination of our basis vectors, which we will use head functions. Of course, it's the same set of head functions which is used for our approximation of our projection, whatever. We just plug this everything in equations, replace blah blah blah, shuffle few sums, and we get this particular expression. And when we have some kind of outer sum of coefficients of this kind of arbitrary test function, but then we have this kind of second term, an integral, which also includes this basis function from our test function, whatever. I think it's related to this Galerkin methods. But anyway, the idea that this coefficient actually is just some kind of, okay, it's a function, but essentially it's a function only of these coefficients which are describing this approximation. So it's a fit coefficients basically. And all the integration, it eliminated all the spatial, in some cases temporal variables. And we kind of rephrasing this original definition, we get this condition that there will be a sum of these arbitrary coefficients for our arbitrary test functions and multiplied by some mi functions, whatever it is. And this whole sum should be 0. And as I see, because these variables are kind of arbitrary, the only way it's possible if these mi coefficients all are equal to 0. And that is to say, we have I expressions that all simultaneously have to be equal to 0. This is exactly what we here see here. So that explains why we kind of mathematically more why we get this particular system. And of course we rewrite here I write the definitions, of course, blah blah blah, nothing interesting. We will rewrite original this definition. In this way we extract everything that's not dependent on spatial variables outside, and we get this kind of expression that reduces to this summation, which is, of course, it looks like a matrix multiplication. And this vector xi is our vector of unknown. So if we get this vector xi by solving this equation, we plug it back into our, it's not interpolation, but whatever it was called, kind of approximation, right? And we get this function approximated. Okay, that's one kind of part which I wanted to touch on, explain. So this is kind of first point, and now we move to something major. which is to say, when I have talked about this procedure of actually finding these coefficients from this matrix M and B, I've talked about more focusing on these head functions, and so I was overly concerned about calculating like both sides, because it's piecewise function. One part of function is on one element, another part is on another element, right? And then we kind of calculated the whole integral. And what the book kind of notices, that we can kind of decompose this matrix into, in this one dimension, in this kind of block matrix with 2 by 2 blocks, and then sum them together. And I said, okay, it kind of looks like mathematically convenient trick, and it's not a trick, as I've realized. These actually blocks are related to our elements and not, so they have kind of proper justification. And how I see it, if we go from viewing this problem from a basis of function view to element view, so this interval, which we'll call element, we just say, okay, first of all, we noticed few important things. When these intervals, they are partitions of a whole domain. That means if we combine them all together, we will recover the whole domain. And the same can be said about these basis functions. They are piecewise linear, and we can also split them. So we can kind of clump them together, relate to each element. So in this case, we just examine one element and every function that exists on this particular element. So this matrix will have some kind of entries M11, M22, whatever. So function phi will be multiplied by itself on this particular interval. The same can be said about this particular portion and then the two functions, right? And they will form this kind of 2 by 2 matrix that is related to this particular element. And then we just construct this big matrix by summing summing over all these kind of blocks into bigger matrix. And this is the general, like the idea of way of thinking when we work with finite element. That we actually have finite elements, a finite element method, not final head function or something method, right? And this approach will be useful in 2 dimensions. So in 1 dimension, it's kind of boring and simple because of how elements are, how they are laid out, that they are basically laid out in a row. We have well-defined neighbors, and so this matrix becomes diagonal, and it's very, very simple. When we move to 2 dimensions, this symmetry kind of breaks. So the overlap of functions, it's not as well behaved, and it won't be. There's no solution for it. So in 2 dimensions, again, we shift to idea of examining one element at a time, but in this case, one element will be a triangle. It might be, of course, a quad or something else, but triangle is the simplest one. And of course, from triangles, you can construct everything you want, basically. So in this case, in the book, they kind of show this particular example of domain triangulation, so splitting into triangles. And again, this matrix will kind of include some kind of head function on node 1, multiplied basically by itself and integrated. This will be this I11 coefficient. But then we should again remember that P1 is linearly kind of piecewise linear, right? And so we have to integrate something that is on part that is on, for example, here on K2 plus integral over K1. So yeah, full entry will consist of how many integrals, how many like triangles are covered by this head function. And this kind of idea that I show two nodes, third is not shown for clarity, but yeah, these are these kind of linear parts in 2 dimensions. These are planes, and they also have, both or three nodes will have height of 1, so it simplifies things greatly. But yeah, it will look like this. We will basically think about this when we are constructing. And so what the book proposes is to deconstruct this huge matrix into parts of matrices that are actually relevant only for particular k'th, some kind of triangle. But we see there is a lot of blank space. It's because these head functions are localized and they don't ever overlap. So for a triangle at maximum, we have 3 nodes. We will have 3 head functions, and then only these 3 head functions on this segment of K will overlap. It's much easier to think this way than to try to focus on a function and then collect all the neighborhood. So in fact, that means that we will have 3 kind of self-integrals, phi1, phi1, blah, 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 so diagonal elements. And then we will have 3 kind of permutations plus this kind of symmetric part, so 9 in total. And all the other spaces will be blank. And so what we can do, we can only focus on non-zero kind of components and calculate them. And the expression will look like this. In just a second. Okay. And so this expression kind of will look like this. Again, I don't really know how they derive it, but let's ignore it for now. So we'll just have this structure when we will have diagonal elements. There's no difference how these elements are permuted in a sense. And what will be different for different triangles is just the area of a triangle. So this will be expression. And again, this is the calculation only of internal, of non-zero components. And our approach will be just to map from this local index 1, 1, 1, 1, 1, 1, 2, whatever, into global matrix. So for it, of course, we know the indices as I will show you how. Of course, we will know just the indices of each triangle, and we will just, this matrix is formed by the ordered row and column as node 1, node 2, node 3, node 4, and so on. Anyway, so we just map the small local matrix into global matrix of particular indices. So if you were using something like Python with NumPy, it will look like slicing basically. And yeah, so we have discussed this. It's an interesting observation that, of course, the definition is completely the same for 1 dimension, 2 dimension, or 3 dimensions. What is, of course, implicitly different is that head functions have different dimensionality, and so the integrals will be not in 1 dimension, but in whatever dimension the domain is. So in 2 dimension xy, for example. And now we will move to actually seeing how this thing is implemented. So we will change some stuff for one dimension. I'm too lazy to make like UI switches. So first of all, of course, we have to prepare a mesh. In one dimension, it is kind of trivial. Let's just say that we have some kind of left and right limits, 0 and 1, and then we generate either using like regular intervals or non-regular intervals, we generate some kind of nodes in there. We will return to this, but what we have to check, how do they implement it in one dimension? I think we already saw. I guess it's mentioned here. Okay, the whole algorithm is not shown, but it's kind of very simple. So okay, Godot crashed. I don't know why it started to happen like this morning. I will restart it. Okay, we will discuss like more advanced mesh creation later. But generally what we should be concerned about is that we will have some kind of mathematical operations that just generate these entries. And for example, for matrix M, this is the procedure, and I'm just replicated it in Godot. I just send some these kind of nodes, I sort them, and then I go through them in order, because also neighboring elements are in order. It is just so simple, right? I go through kind of n-1 elements, and then I add to this matrix particular values. Okay, in Godot, of course, you will need a linear algebra library, and you will have to do something crazy like this. There's no like proper matrix additions or support for slicing for matrices. So you have to do it very old school. For example, like take old value and increment it or something. But still, kind of this is easy to understand. There's also a definition for, basically that's what they do in MATLAB, right? For B, they have also kind of this integration formula, trapezoid rule. But again, same stuff, different widths of elements in this case may affect this. And let's see. I have this kind of switch to use simple or more advanced method. And what we have to see, of course, it's the same curve as we had in first video. It's rescaled a bit in y direction because of just plotting stuff. So yeah, this is the same function. It shows you the, okay, it just shows you the L2 projection. Maybe what may be curious is to reduce number of elements, and for example 6 as in presentation, as in the book. Okay, it looks hideous, but I guess it's exactly the same what is going on in the book. What I wanted to show you is like mesh. I don't know why it outputs like so many elements. Anyway, I just wanted to show you that the mesh was diagonal. It's just the layout of elements is such. So now we will move to actually doing something more advanced. And it might this approach, it might seem weird, but we will do something as follows. So we will create, although we can pre-generate mesh, right, and it's just a collection of ordered nodes and just send it to this procedure, we will actually approach it differently. We will do, as I call here, like generation by node insertion. So that means that we will gradually refine the mesh. And so how you should think about it, then we define a initial domain. In our case, it's like 0 to 1 or something. We have pre-generated a bunch of intermediate nodes, and then we take first node, and then we kind of ask, we will split this kind of original domain using this node. Just for clarity, I will pick the middle node. Of course, it can be anything. So we will kind of split it. Okay, I will draw the splits. I will call them children. But there's one part missing, actually, which is kind of trivial in first iteration, which is saying which this element is node a part of. So of course, if we have only one element, it will automatically understand that it should split exactly this element. So yeah, on the further steps, for example, second point, it generates, point should be somewhere here. Which element is this point part of? And so here we will employ this interesting recursive algorithm for searching. Let's first of all like think, okay, let's assume that we know which element it is part of, and it did a split. Maybe it also did a split here or something, split here, whatever, just random. And for example, it's some kind of third point or something. And again, I'm adding, I should ask which part, which element, which active kind of element it is part of. So in one sense, I have to evaluate all these kind of latest elements, which represent like the latest state of this mesh. And then I should go through them. For example, point should be here. It will go through here, now, here, not, here, not, here, not. Maybe it's here. And then if it's not here, it will automatically assume that node should be in this mesh. This is one point. But if we had a lot of splits, the number of elements that had to be checked will be huge. So what I propose is this kind of recursive search algorithm. When we start from initial kind of level, which enveloped all the whole domain, and we say, okay, if it's in this element, I check its children, right? It checks like the left child, and if the point is not part of this element, it will automatically assume that it's part of this element, and it will check its children. And at some point, it will actually find the last element, and this is the element which doesn't have any children. And you see the recursion actually, if you like examine this particular structure and our approach to its analysis, we have this kind of self-similar blocks in this layout. So in a sense, we apply first kind of recursion on this block. It guides us to second level of recursion, which does exactly the same analysis on a second block. So I think it's very beautiful and it's fast. I mean, there are other options how to do it. For example, you pick a random element And then just by examining the value of this point, you know whether you should go to the right or to the left. That is another option. So that means you will have to have neighbors to understand in which direction to search. But this is the alternative, and I like it way more. But we will accommodate possibility of using two approaches. So now let's just examine how it's done. Again, we return to our mesh generations. We have inserted the left and right point. We will need values, like function which we approximate values on these particular points, and why not do it right now when we're inserting them, right? And then there's the question of how do we actually now store this data. And my approach, which will be useful primarily in mesh generation, but also like as a whole package. Here's kind of a bit of simplified version, but we will store list of all existing and previously existed elements, again, which we will use for this recursive search. And we will fill them in the following order. Left and right element will be kind of pointers to nodes in a list of nodes. So if you notice that we have one kind of expanding list in which we place nodes, they get the ID by their order number. And so here we place just this kind of so here, okay, it's a bit confusing, but certainly left node will be with index 0, right node would be within index 1. It's not correct here. It's just coincidence. But yeah, I use indices because when we transition to 2-dimension and possibly with 3-dimension, entries here will be actual vectors. So instead we can keep, and also this is approach, like when you work with meshes in rendering, on GPUs, whatever, it's just common approach to send all the nodes on your GPU and only use references as indices, because GPU don't really understand references as such. Kind of we will keep track of which element is our neighbor to the left and to the right. We won't use it, but it might be useful. And these will be indices in the list of this element data. And what's most important here also is the children, left and right. And that time we have split it into left and right. This will be indices in this particular data storage. And additionally, we will check the widths of all elements, just so it's faster and easier to access. And then we have to create, for example, in total we have number of initial nodes, whatever, 2 we have added, and the remaining n-2 we will fill. And it will be filled in buffer, because our point insertion will be kind of a while loop, like here. And so while there are remaining nodes in a buffer, we take out whichever we want. In this case, it's a less node. I prefer it because it avoids like some kind of memory shuffling. It just reduces the memory like this. And we have this described algorithm of actually finding which element is this node part of, and then splitting into 2 children. And let's examine how this recursive element is organized. First of all, I give a point and I don't give which element to search. It starts searching from element 0, which is the whole domain. If it's a first point, it will not have any children, so it will return this 0th element and it will split the 0th element. In case it has children, it will determine whether the point is in a left child if it's not here, it automatically understands that it has to search the right child. And so it applies this recursive search on particular child which has this element, right? And at some point it reaches this element that doesn't have any children, and it returns it, and it returns down to stack this element. So we got which entry in this element's data storage. We have element, and then we kind of do a split. Of course, the split is just a manipulation of data. Just some observation, few observations. Of course, left and right node will be inherited by left and right element, and the middle node will be also inherited by, not inherited, but used by these two elements. It's just really trivial. Again, we add this node to nodes. We evaluate this kind of function, approximation function value. Then we add new elements, which again are IDs are just their order. And then we know that we add two elements, and we can understand which IDs they will have. And that's what we basically inherit the left node of one element. Right is our node that separates. Kind of we can inherit neighbors. We said that we don't have any children, blah, blah, blah. We append widths. We can replace the width of original of their parent as -1 if you want. Now what's important, we replace parents, children from like -1 placeholder, which means that they don't have any children, to actual children. And that's what happens recursively, right? When the last node is processed, buffer becomes empty, and this process stops. Now notice the order of elements in this data structure. Of course, it also contains everything, even like non-final elements. But the order is messed up. Although in here I kind of fill them backwards, but it doesn't matter. It is not ordered as originally. And so we have to actually deal with it, and it becomes a problem actually in 2 dimensions, as we will see, but this approach will solve it. So again, let's return to solve. And that's what we did. We kind of generated whenever it is this mesh. We just extracted elements that actually don't have children. So in this case, all are negatives. All last elements are negatives. Let's ignore sorting and resorting for now. And this is our procedure. So remember how this looked. The regular approach simply manipulated entries. So here we return to this idea of actually like linking, like only using like local matrix 2 by 2 in this case, and then just using node IDs to actually place it in a bigger matrix. And so, well, this is the idea. We just go through all the active elements, not functions anymore, not ordered, doesn't care. And we just set particular elements, and this is the function, right? We have pre-generated this particular matrix Mi here, filled it with correct entries, divided by something. And then we just kind of go through this small matrix, take its element and take a global reference, which is like the actual node number, and place it into a bigger matrix. So M large. It is exactly what happens. It's the same with B, load vector. except here we also have to supply values at nodes. That's why we needed to gather them. We could have like evaluated them, I don't know, it doesn't matter, it's just easier that way. And our solve method, here's a bunch of useless BS. The idea, of course, is just we use linear algebra, this add-on, this package, to get an inverse multiplied by b, and we return this xi coefficients, which of course are kind of approximation fit coefficients. What I do next, now we have to kind of visualize them. I prefer in this case to bring them in three-dimensional space. That means I have to actually draw like mesh, like polygons. So I create these 3D triangles in space, but it's not important. You can do it in 2 dimensions using like lines, polylines on canvas. But generally, yeah, what I have to do, roughly speaking, is I have these kind of upper nodes, I generate the bottom nodes, and then I generate triangles. I say, okay, this node, this one is one triangle, this node, another triangle, right? And here we have, for example, 5 elements, we will have 10 meshes. So this kind of explains how to do this L2 projection if your elements are not ordered. And this is exactly, of course, the case in 2 dimensions. And now we will really briefly look at it, how it works in 2 dimensions. And I guess, you know, spoiler alert, nothing changes because we kind of solved all the problems. Although now we face like a bigger problem because generating mesh for 2 dimensions, it's not as trivial. And I will not use like a real algorithm here. I will just use some kind of basically a placeholder, right? And so this will be my approach for this particular task. I will generate a grid of triangles. So I will pre-generate nodes in 2 directions. So here it's an x and y. And then I will create this triangle by just by observing the structure of this particular, you know, node layout. Again, we have to reference nodes as they're flattened. So 0, 1, 2, 3, 4, 5. So that means I have to understand which kind of node is here. Just by like playing around with indices, understanding that like this node 0, 1 is like four nodes in this direction, like one layer times, so 1 times how many nodes here plus 0 here, and here plus 1 or so. Anyway, just by manipulating with these indices, we can like construct this kind of triangle data, whatever. It's really kind of simple, although it's a bit tedious. Now, if we want to recover neighbors, which we don't use, yeah, it gets a bit more complicated, but again, you can make some, you can have some insights by just like considering that these are individual boxes in which we have 2 elements, and then like box 5 will have like elements 8 and 9. It's like 5 minus 1, everything times 2, because there's 2 triangles. Anyway, you just can easily reconstruct it. And that's basically what we get. Our mesh, regular mesh, equal like triangles. I have only active elements because we didn't do any refinement. And as these functions like look exactly the same, and they in fact they are absolutely the same except for the number of nodes that we are passing. So here we have 3 head functions living on top of these nodes. Like this, there's really there's really no difference, but we have like interval widths, and then now we have areas, and then we have like slightly different coefficients for our smaller matrices. For one dimension it was 1/6, here it's 1/12. Nothing really changes. I just copy pasted them and changed just A to H basically. So this is the nice thing. And let's see how it will look with, oh, the grid is still pretty refined. Interesting hanging point. I wonder what it is. Yeah, but generally that's why we want that's the goal of this video. Okay, maybe some additions. I did some tests. For example, for one dimension, when I manually reordered, I did our procedure splitting, and then I did reorder all this data structure as in simple case in it. What it did, it shuffled columns or rows, whatever, of these M and B matrices. In this case, M is more important. It just made them diagonal, and that's all the difference. And it is true that it's easier to solve like more diagonally dominant matrices, depending of course on your approach, but essentially nothing changes. You're just solving a set of equations which are presented in different order. It means that they will have the same solution. It might be just more difficult to find. So let's see. Did I cover everything I wanted? Okay, this again, this last point was really trivial because we have prepared everything in one dimension when it's much easier to understand, but essentially it does exactly the same. Well, let's go through. I don't know, and maybe some just comments. So here I just show you that how to get a system of equation, at least my interpretation, how it's done, and that we notice that exactly what I was talking about. The definition is exactly the same for one dimension and two dimension. I guess this is the observation. The transition of thinking about elements, so iterating through elements, it simplifies things a lot. And it is more generalizable to higher dimensions. Again, definitions are the same. So in one dimension, although it looked like very simple, when in practice you want to actually solve 1D and go to 2 dimensions, it gets so much harder, especially if you want to start thinking about writing your own measure, which we'll do in next video. It's already done. I think it's pretty interesting, and I have a few interesting visualizations. So yeah, here we have talked about this interesting idea of using this recursive search. It will be used in meshing. Again, spoiler. Maths, pretty simple, not that different than book example, except that we are just redirecting our local matrix elements into like global matrix. That's it. And this information is carried by nodes, triangle nodes. In 2D, okay? Very simple. So I hope it was interesting. I think methods were kind of fun. So yeah, let's see you next video when we will discuss Delaunay triangulation. Thanks for watching.